Hello everyone, I'm Priyanka, a PhD student at Dr. Khan's lab at Georgia Tech. Today I'm going to be presenting my work on comprehensive time-dependent dielectric breakdown characterization of ferroelectric capacitors under bipolar stress conditions. We all have seen that AI has been growing exponentially in the past few years, and that's evidenced by the increase in the model parameters over the years. Here we have the plot of the model parameters with each passing year, and we see that there's a exponential increase in the number of parameters. And to keep up with this workload demand, hardware has also been scaling, and it's both in the logic end and the memory end. In the logic end, we know that the transistors have been scaling exponentially year after year, and on the memory end, each layer of memory, that is static RAM, dynamic RAM, NAND flash, and hard disk drives, have also been scaling exponentially over the years. If we look closer at the memory regime, we see that at the bottom end we have SRAM with high access speeds and low bit density, and on the other end we have NAND and HDD with low access speeds but high density. And we notice there that there are gaps in these memory plots, and with the advent of protocols like Compute Express Link and emerging memory technology, we're no longer restricted to these particular access time and densities. What we can do now is use these emerging memory technologies to bridge these gaps, along with the help of protocols like Compute Express Link. And a testament to that is the recent demonstration of a 32 gigabit non volatile DRAM using ferroelectric materials. This was demonstrated by Micron in IEDM 2023. So, uh, so what is ferroelectricity? Ferroelectric materials are materials which have a non-centrosymmetric crystal structure, as shown over here, with the center atom being displaced from the center, leading to a dipole being created. And the interesting thing about these materials is that they can be switched between one state to the other using an external electric field. Here we have ferroelectric material with multiple of these dipoles, and when one electric field is applied, it's pointing in the downward direction, and when electric field of the opposite direction is applied, the polarization switches to the upward direction. So if we look at the polarization voltage curve over here, we see hysteretic behavior. Ferroelectrics have come a long way, and in the last 12 years, they've become more and more interesting. In 2012 2011, uh, ferroelectricity was discovered in doped hafnium oxide, which is CMOS compatible, hence opening up a large array of possibilities for these materials in our current computing technology. So, since then, into a lot of progress has happened, and in 2023, we have seen the demonstration of a 32 gigabit DRAM. But these devices still have some challenges that we see. So we want low voltage operation, and we also want to increase the reliability and endurance of these devices and reduce the device to device variation. In this talk, we're going to focus on the reliability and endurance of these devices. So if we look at dielectrics and look at the charge versus voltage characteristics, it follows a straight line. That is, as we increase the voltage, the charge increases in either direction. And from the very well studied percolation theory for these devices, we understand that as we stress this device, defects form in the bulk of the dielectric and eventually lead to a percolation path that manifests as a short across the two electrodes. But in ferroelectrics, if we look at the charge versus voltage diagram, it shows a hysteresis, meaning that when a voltage sweep is applied, that is between positive and negative voltages, not only do we have the charge changing, but we also have the polarization switching that is occurring. So this makes these ferroelectric devices fundamentally different from dielectrics, and that warrants separate study in terms of reliability and endurance. So we're looking at bipolar stress over here because that's what is relevant for read and write operations for memory applications. So what we're doing in this study is trying to understand the breakdown mechanism for ferroelectric capacitors by looking at the voltage and temperature acceleration. In order to get there, we look at these devices that is hafnium zirconium oxide layer with tungsten electrodes. We have a TEM image of our devices, and we see here that the TEM confirms the crystallinity of this layer and also confirms the thickness of the layer. And we connect the bottom and top electrodes and apply a voltage across the two electrodes. And if we see here, when we apply a very low voltage, there is no ferroelectric switching that we see in this PV diagram. And we also confirm this by doing a positive up, negative down measurement, which extracts the polarization switching while removing the effects of the background dielectric. So for very low voltage, we see next to little polarization switching. And as we increase the voltage being applied across the electrodes, we see the hysteresis opening up and the remnant polarization value increasing. So if we go further, the polarization increases further and the polarization value eventually saturates to a certain value. So we take these devices and stress them using 200 nanosecond bipolar pulses, and we first do that at plus and minus 2 volts, and we take the pristine device and do a PV loop measurement, and then stress this device and then do another PV loop measurement and continue this until the device dies. So here we see that we've done a PV measurement and followed by 10 power 2 cycles, a PV measurement again followed by cycling again. So this is the pristine PV loop, and as we cycle the device, we see that the PR reduces. Here we've plotted the PR with respect to cycle, and as we continue to cycle, the polarization value keeps decreasing, and if we continue cycling, the device eventually breaks as indicated by the sharp increase in the PR value. This essentially means that there is a short between the top and the bottom electrodes. So this was done for a particular voltage case, and to better understand the underlying mechanism behind this dielectric breakdown, we did this cycling study at different voltages and at different temperatures. So here we have the polarization versus cycles curve for multiple devices overlaid on top of each other, and this is for the 2 volts case. We see that the polarization value decreases and then breaks down, and we see that there is a distribution in the dielectric breakdown for all these different devices. So not all the devices do not break at the same cycle, and there is a distribution for where it breaks. And as we reduce the voltage, the number of cycles to which the device survives increases, and for 1.4 volts we see that the cycles goes beyond 10 power 10 cycles. And this was done at 25C, and here we have increased the temperature and then done this same study, and we further did it for also 110 degrees Celsius. So we see that there is a distribution in the cycles to break down, and this can be represented using Weibull plot. That is, we plot the Weibit of these of this distribution over here with respect to cycles to break down, and we see here that all of these fall in a straight line, indicating that this distribution indeed follows a Weibull distribution. And this is for the 2 volts case, and as we reduce the voltage, the graph shifts rightward, and eventually for 1.4 volts it goes over here. So this can be represented also for the other temperatures, and this clearly shows that there is a shift in the distribution as we change the voltage and the temperature. So we've looked at the distribution, but now let's focus on the average value using the Arrhenius thermochemical model. So here we see that we have a pristine device, and then at the other end we have the broken device. So what we can do is model this by using a barrier. So we have the pristine device on one end, and as we apply some stress, it crosses the barrier and goes to the broken down state. And this barrier to break down is reduced by increasing the voltage. That is, as we increase the voltage, the device becomes easier to break, implying that the barrier to break down is reducing. And this effect can also be brought about by increasing the temperature. That is, as we increase the temperature, the, the barrier to break down reduces and the device becomes easier to break. So here we have the expression to explain this exact phenomena. That is, we have 1 by cycles to break down, represented by uh, two different terms. So here we have the electric field dependent. So from this expression, we can extract something called the effective activation energy. That is the exponent, the numerator of the exponent with kT. So we have EFE into alpha minus EA, and we see that when we plot the 1 by CBD with respect to temperature, we have straight lines. So we have for the 2 volts case an effective activation energy of 0.35 electron volt, and as we reduce the voltage, the effective activation energy increases. So this is as explained in the previous slide, that as we increase the voltage, the barrier to break down decreases, and that is represented by this effective activation energy. So we can also extract the field acceleration factor. That is if we plot 1 by CBD with respect to electric field, we again see that these points fall on a straight line. So we have the lines for 135C, 110C, 85, and 65 degrees Celsius. And we see that as we increase the temperature, the field acceleration factor reduces. So we've talked about the effective values, that is the effective activation energy and the field acceleration factor, but each of these individual constants also hold meaning. So we have intrinsic activation energy EA, which is the intrinsic barrier to break down when no voltage or temperature is being applied. And we have alpha, which is the bond polarization constant, which is indicative of the polarizability of the material. And since it's a ferroelectric material, we expect this to be very high. And we have gamma naught, which is the field acceleration constant, which is indicative of the trap generation energy during the breakdown process. So, in order to put these intrinsic values into perspective, we've compared it with silicon dioxide from literature. And we see, if we look at the effective EA plot, we have effective EA with respect to electric field over here, and we see that HZO values are lower than silicon dioxide, and the line is steeper in the case of HZO. And if we look at the field acceleration constant, we have HZO, which is higher than the silicon dioxide and with a steeper curve. So we have HZO over here and silicon dioxide over here with the gamma naught alpha in EA values. So if we look at the gamma naught, we have 0.32 for HZO and 2.4 for the silicon dioxide, indicating that it is much easier to generate traps in the ferroelectric with respect to the dielectric. That is, the trap generation energy is lower for HZO. If you look at alpha, it is significantly higher than silicon dioxide, which it's understandable because HZO is ferroelectric while silicon dioxide is dielectric. While we see that the intrinsic activation energy is roughly the same for both these devices. So what's happening is that while the underlying mechanism for silicon dioxide and HZO is the same with respect to breakdown, the breakdown in ferroelectric material is being accelerated by the polarization switching. So we clearly see that these two terms are what are accelerating the dielectric breakdown. That is, they are way more sensitive to electric field and also way more sensitive to temperature. So we see that although there is polarization switching present in HZO, the rough trends in these effective activation energies and field acceleration factors are the same. That is, we still see linear behavior, but this acceleration is being this cycles to breakdown is being accelerated by the presence of polarization switching in hafnium zirconium oxide. So, to conclude, the trends in voltage and temperature acceleration in both materials are the same, but hafnium zirconium oxide has a lower effective activation energy and higher effective field acceleration. To summarize, we've seen that we've taken a pristine device and subjected it to bipolar cycling and eventually leading it to its breakdown. And we've modeled this using the Arrhenius thermochemical model, which explains how temperature acceleration occurs with voltage and temperature increase. And we've measured multiple devices for a range of different voltages and temperatures, and we see that they can clearly be modeled using the Arrhenius thermochemical model. And we see that although the underlying mechanism seems to be the same for the ferroelectric and dielectric, um, the cycles to breakdown is being accelerated in the case of the ferroelectric by the presence of polarization switching.